So the idea is people can interrupt him whenever they want. It's really supposed to be freestyle. I mean, I think he'll give another seminar tomorrow, which will be a Blackboard seminar, which will be even more time for questions. But the idea is that he's going to talk for about an hour, and if he's interrupted with lots of questions, he'll go over time. So go ahead, Danilo. Whenever you want to start.
Okay, thank you so much for inviting me to give this talk and for the introduction. I'm truly honored to have the opportunity to speak here, even if remotely. And for those of you whom I have not met, my work focuses on statistical mechanics, with particular emphasis on what we call soft matter. Though I like to think I'm in this blurred and yet rich interface between soft and hard condensed matter physics. As you can infer from the title of my talk, I'm particularly fond of these two branches of mathematics. And I should say that there are few scientific fields of soft matter in which these concepts from geometry and topology are so visually explicit. Now, there's another aspect I would like to emphasize about my research, and that's encapsulated by the term disorder, which quite often carries a negative connotation. But that today, I'm going to discuss two situations in which disorder is intrinsically connected to the emergence of complex, interesting phenomena. In the first part of my talk, I'm going to talk about some intriguing layered liquid crystals and their beautiful focal conic defects, and then explain this material's microstructure using theoretical ideas borrowed from a very disparate system. And then in the second part of my talk, I'm going to show how to use periodic lattices to describe transitions to a disordered solid state, and then discuss their universal scaling behavior and applications ranging from colloidal suspensions and metamaterials to strange quantum liquids. So let me talk about schematics, and I'd like to start by thanking my collaborators for their invaluable work and critical input. Suppose an experimentalist takes a sample of this schematic fluid, it's a kind of soap, place it between glass slides, and then observe it with a microscope. At high temperature, there's not much to see. This is plain, highly symmetric isotropic fluid. If you could zoom in, you would see a bunch of molecules that try in vain to align themselves along the same direction. But here the temperature is so high that there's no longer range orientational order. As you lower the temperature, the rotational symmetry of this isotropic phase is broken, and you start seeing structure of the nematic phase. If you could really zoom in some region here, you would see that now the bunch of molecules bump into each other are generally oriented along some director field. Still, not everything is perfectly ordered here, and there are some clearly visible topological defects, which I'm not going to have time to discuss in this talk. Now, here's what happens if I lower the temperature even further. This is what we call the schematic phase. See how organized the structure has become. Now look at those lines. They do look like ellipses, right? And in fact, I can actually draw a real ellipse there. And just for the fun of it, I'm also showing one of the ellipses foci right at this X point here. But then you might be thinking, what are those shadows that are coming out of the ellipses foci? Apparently, I can not only see the ellipses, but also one of their foci. And that might look very strange in some sense. Now, suppose I could zoom in and look at the structure of this schematic. What would I see? So for the next few slides, I'm going to discuss how these ellipses arise, what the structure is, and then I'm going to combine continuum theory and GPUs to simulate and get a deeper understanding of this remarkable phase. So old George Friedel was one of the brilliant scientists that looked at the two-dimensional schematic texture more than 100 years ago. I must pause here to say that high school mathematics education in France must be outstanding, because Friedel looked at this texture and inferred that the conics that he was seeing were the directrices of a set of equally spaced channel surfaces named the Cyclides of Dupin. Now, in other words, he inferred from pictures like this that schematics formed equally spaced layers. I think that's a remarkable example of deep geometrical reasoning leading to rather non-trivial physical insight. So let me go over this slowly and start just with 2 dimensions. Suppose we want to draw a set of equally spaced curves in the plane. For a straight line, this is very simple, but let me illustrate the process. You draw a set of normal lines to each point in this curve. And then you walk a fixed distance, say delta, along the normal line. As you keep going, you end up with a set of parallel straight lines filling out the plane. That's very simple, but what if you start with a curve that's not straight? Now the normal lines are no longer parallel. They spread or get closer to one another depending on the curvature. If you indulge me for my limited skills with PowerPoint drawing, I hope you can see that you still can use the same process and draw a bunch of generally equally spaced surfaces in the plane. Now, it's not hard to see that as you continue this process, eventually you hit a point where the curve develops a cusp. This is a singularity. And if you think of optics, for instance, you quickly realize that light scatters wildly at those points. There's actually a whole theory describing natural focusing and singularities of caustics based on these ideas, which I have not time to discuss in this talk. Instead, I'm going to ask what happens if I do a similar construction in 3-dimensional space. Certainly, I can define a unique normal line at any regular point of the surface, and then determine a set of equally spaced surfaces using the same process that I have just described. Perhaps the simplest example arises when you try to wrap tori over the same singular circle, as is shown in this figure here. Eventually, you will develop a pair of singular lines. We call them focal conics. Here, they are a circle and a straight line passing right through its center. There are more general cyclids in which the singular curves are general pair of conics, as in this case here. Remember when I said that we could not only see the ellipses, but also one of their foci? That's because the singular hyperbola here passes right through one of the ellipses foci. So at long last, we have learned what these matrices are. They are viewed as intermediate states that break the rotational symmetry and translational symmetry in 1 dimension of isotropic fluids. There's still liquid-like behavior within its layer. Now let me come back to the Jane's beautiful image, and we understand what the structure of one pair of focal conics is, but then how do these focal conics combine to form this magnetic microstructure? And also, what are all those regions that do not show any ellipses at all? When I came to this field, there were more than 100 years, of course, of beautiful theoretical and experimental work done on schematics. Yet there were no simulation results that would spontaneously lead to these focal conics and that could shed light into the inner structure of the schematic state. So the first thing that I did when I went to Cornell to work with Jim Sethna was to set up simulations for these systems. We wrote down an elasticity theory for schematics in terms of a vector field, capital N, that's associated with the local normal to the schematic surfaces. These 2 terms here penalize the curvature of the layer surfaces. They're separated in the standard way, with one term representing the mean curvature and the other term represents the Gaussian curvature. And here I'm showing what this decomposition looks like in terms of this magnetic layer normal field, which is the main quantity we want to study. There are some caveats that I'm not going to discuss, but for the specialists in the audience, this is pretty much what the splay and saddle-splay terms of the Ozane-Frank free energy of liquid crystals look like. Now, the first term penalizes the compression of the layers, and it's given by the equation, by this equation in terms of the layer normal field. There are alternative ways to write down this elastic free energy that I'm not going to discuss here, and that give essentially the same qualitative results that I'm going to present. Now, in the next step, we set up dynamical equations by using a gradient descent approach. Note that all this is doing is to drive the system to the minimum of the free energy. But again, for the specialist, this equation is a simpler version of the Leslie-Erickson theory of liquid crystals. With the equations of motion set into place, we wrote a code using CUDA to run our simulations on GPU cards. And then we generate some random initial configurations and numerically solved for the time evolution of our fields. Here's an example of the time evolution of a two-dimensional section of a three-dimensional schematic simulation. What I'm showing here is a visualization tool that we developed to mimic microscopy images at the schematic stage, with the microscope focused on one of the glass slides. This is a nice place to focus when one considers planar anchoring of the schematic at the substrate, meaning that the layers are perpendicular to this glass line, forcing the singular ellipses to be there. As you can see, the focal conics spontaneously merge in our simulations. But now that we have numerically produced focal conics, we can take the obvious steps of simulating schematics under many different circumstances. I'm not going to discuss this here today. Instead, I'm going to leverage the simulation results to explain the rules governing the schematic microstructure. See these ellipses and how they are organized. The schematic structure seems to be composed of a mosaic of low energy configurations called focal conic domains. Now there is another well-studied system in which coexisting low energy configurations merge, interpolate, and lead to non-trivial structures. They are called the Martensites. So there are many kinds of Martensites, but let me remind you of the cubic to tetragonal transformation, which is easy to explain and visualize. In this example, the important idea is that there is a class of crystals whose cubic unit cell deforms into a tetragonal shape at low temperatures. As you can see, this deformation can take place along any of the three Cartesian directions. And if you look at the free energy landscape of the system, there is a single global minimum for T greater than Tc, as shown here. And then there is a first order solid to solid transformation leading to three minima for T smaller than Tc. Now suppose you let your crystal undergo such phase transformation while you constrain the boundaries of the system so that there is no net strain. Some regions would like to deform along one direction, other regions will deform along other directions. And near the boundary of these regions, these variants will rotate and form these twin boundaries and fine laminate structures to accommodate the cell deformations under constrained boundary conditions. You can actually see these twin boundaries using experiments, for instance, as shown here. Now you might be asking yourselves, what does that have to do with schematics? So in the following slides, I'm going to discuss how a generalization of the theory of Martensites gives an explanation of the schematic microstructure. There are three elements from this theory that I'm going to discuss: the variance, or low energy configurations, the symmetry of the energy minimizers, and compatibility conditions to correctly combine the different variants. I've already described the three variants in the case of a tetragonal Martensite. They correspond to configurations along the three, to deformation along the three Cartesian axes. In principle, one can assign distortion tensors to each of these configurations as shown here. So you don't have to pay too much attention on those matrices. They are there just so that I can refer to them later. Now, the variant we choose to describe schematics are much subtler. They correspond to low energy configurations described by these toroidal focal conic domains. In the same way that I can define distortion tensors for crystal Martensites, I can define my schematic variants by a function phi characterizing the tori. This function is chosen so that its levels determine the layer surfaces. Because there are two possible choices for the sign of this function, we choose the sign of phi to distinguish between the two variants. These extra 5 variables are a little bit hard to visualize in 3+1 dimensions, but it will become more clearer when we restrict our attention to planar sections of symmetrics. Now, in
Sorry,
two
can I
dimensions,
ask a very basic question just to make sure that I'm
absolutely.
following?
Yeah.
So the microscopically we have these molecules that are elongated, right?
Yeah.
And then if I were to look in this yellow picture, they would be going around the circles of the tori.
That's
true?
correct.
They are oriented locally, they are parallel.
They are normal to
locally,
those
go around.
surfaces. They are normal to those surfaces, the yellow surfaces.
Ah, they are normal, not tangent. So
Not tangents, they are normal, yeah. So they are, for instance, here they are radially oriented here with respect to this section. They are normal to the surface.
And the ground, they want to be parallel, right? So the ground state would be, one ground state would be all parallel. But
that's
they
correct.
could have
a bunch
black...
of spectra, yeah. The ground state, let me see if I've shown this, maybe I didn't.
The black,
here,
the black curves there.
This is like what they look like and in the ground state. You see you have a set of planes that are parallel, and the molecules are perpendicular to the planes, but within each plane you have some liquid-like behavior. Okay?
Yes.
Sorry,
And then you are simulating the geometry of these planes.
That's correct.
So you are
So
figuring out...
we have a continuum theory that describe these surfaces, yes.
Danilo, I have a question. In the case of the liquid crystal, all of the interactions are short-ranged.
That's right.
In the case of the solid, you have to deal with the elasticity, the elastic interactions, which are long-range. Is that, does that make a big difference to this?
For what I'm gonna use
length
here,
scales will change enormously because of that.
Say that again. I didn't.
The length scales will change greatly because of that.
Oh yeah. Okay. So we're gonna use the same framework, but there are some differences. I don't think that's gonna matter for the kind of analogy that we're gonna draw here. But you raised a good point. That's a good point. But for the ingredients that we're going to use to describe this matrix, that's not going to be important. The fact that it's all the interactions are local for the liquid crystal. But that's a good point.
And sorry, just one more question so I understand. So the black dot in the black line, there would be energy stored, right? It's like a vortex. So there locally there is some...
Yeah, there is some defect there. Yeah, that's correct. Yeah,
but not at the red line, right? At the red, or also at the red line. No.
Also the red line have cusps as well. Yeah,
the red line.
There is energy. Like they are singular, and the molecules don't like that region as well because they form cusps there. So there is some energy cost in the red line as well. And if I could show this in 2 dimensions. We can look for pictures in 2 dimensions, and it's clear that I don't know if you can see my fingers.
Yeah, I can.
That the planes look like this, and they form a cusp. So there is some frustration for the molecules as they get close to this singular line.
Okay, and then one more naive question. So, and then these configurations, they freeze in these positions that you found with your simulations, right? And we are not studying the dynamics of these surfaces.
Okay,
right?
okay. So no, we're not studying the dynamics at this part. And that's a good point, because if you look at the experiments, they are pretty much stuck on some configuration. Right. Not all of our simulations led to some stuck configurations. They were still evolving, but they were evolving very slowly. So for all the purposes, they were frozen, but not exactly. It was more like they were in some metastable state that wasn't able to jump into some lower minimum of the free energy or something like that.
And then if I increase the temperature a bit, can I at some point start thinking about these black and red lines as particles and have a quantum field theory for them, and or no?
That's a good question. I don't know.
Sorry, but in some sense, these are is not an equilibrium state that you have here.
In some sense, so if you're talking about the experiments or the simulations, because in the experiments there are some situations where you can completely stabilize these focal conics. If you, depending on the boundary conditions that you have in the two glass slides, they get completely. I mean, it is the equilibrium state because you added some frustration by having different boundary conditions on the glass slides. One example of this is that you have your layers to be perpendicular to one boundary conditions and parallel to the other. Now, this will make the situation more complicated and favor the emergence of these focal conic domains, even in complete equilibrium. It's not, right?
So I was also worried about this question of whether we're in equilibrium. You wrote down a dynamics which is just gradient descent, right? There are no fluctuations. So in some sense, the density of these defects is then determined by your initial conditions plus your boundary conditions, right? At
yes,
least
that's correct. Yeah, that's right.
So are your initial conditions essentially, are you basically quenching from infinite temperature or?
No, that's a good point. And yeah, most liquid crystal specialists always ask me about which I'm not sure that's not necessarily your case, but always ask about the initial conditions that you're considering. We do have some length scale for characteristic length scale for the ordering of the system at the initial condition. It's not a completely isotropic system. It has some order over some length scale that we begin with, and we start evolving it from it. It looks more like a nematic. It's not exactly a nematic because I'm throwing away all the terms that are important for nematics, but it looks a bit like a nematic at the beginning, then I quench it to a low temperature in this metric. That's what we're simulating.
And so I'm not a liquid crystal expert, so I don't actually know how the experiments go. And I guess what I'm wondering is, since, if the dynamics are gradient descent from some reasonably random initial condition and so on, do you get the density of these things right? So I mean, we're going to explore all sorts of interesting structures, but
yeah. So the density
is the number of them. Does the theory get the number of them right?
That's correct. Yeah. So one thing that happens in our simulations, for instance, is that there is a characteristic length, which is the gap between the two glass slides.
Yes.
And this gap determines what the size of the focal conics is. So basically, our focal conics sizes will be determined by this size of the gap between the two glass slides. And we do observe this in our simulations.
And that's also true experimentally?
That's also true experimentally. Yeah. Experimentally, there are some more complicated situations where they form. You have a bunch of focal conics forming polygonal domains and things like that. And the size is all determined by this gap size between the two slides in most experiments. Of course, I'm talking about one class of experiments. There are other experiments that show other kinds of structures.
Okay, I have more worries about this, but we should let you go on.
Okay, so I was here talking about the two-dimensional version. And for the planar section of SMACTs, they correspond to cones pointing either upward or downward. And just as a reminder, planar sections are the two-dimensional sections in which the layers are perpendicular to the section. Now, once we have determined the variance, we can describe the full set of energy minimizers for the systems. For crystal Martensites, you can perform a three-dimensional rotation of these tetragons, and that will not cost any energy. So the energy minimizers correspond to the union of the sets of arbitrary rotations applied to the distortion tensor that I described earlier. Now the set of low energy symmetries for
Sorry,
spectricals.
at this level, why is it SO3 and not the point group symmetry of the crystal?
No. So okay.
How continuous rotation?
Okay. So this is mesos. It's not the microscope. I'm considering here, for instance, these are the distortion tensors.
Yes.
And the only thing that I'm considering here is that I can, once it deforms along these tetragonal shapes,
Yes.
I can generally rotate this. This can be regarded as an elasticity theory instead of the original microscopic theory.
I understand, but in a cubic crystal, which is where you start, the symmetry is actually lower than that. I mean, if you go beyond linear elasticity, you will see them. You see terms in the free energy which are not invariant. So is the symmetry discrete or continuous? It makes a difference. So in other words, I'm going to have domain walls between things oriented this way and that way, or you will go continuously from one to the other? Is there going to be an energy cost, in other words?
Say that again, I didn't
Is there
hear
going to
you.
be a free energy cost for rotating a domain from one direction to a perpendicular direction?
So it doesn't have any energy cost to rotate the domain from one direction to the
I mean, at if I try to, if I rotate the entire sample, of course, there is no cost.
Yes.
But if you have a region of space and you try to orient of the crystal, you try to orient it along a direction which is not one of the crystalline axes, it's going to cause.
Yeah, that's true.
So you expect the free energy to be invariant under the point group symmetry, not under SO3.
No, that's true. In general, that's the case that you. But here I'm talking just about the rotation of the entire variant, not the point group symmetry of the system.
I understand you want to do a macroscopic analysis, but even at the macroscopic level, particularly systems with long-range interactions, the fact that the symmetry is actually not continuous matters, I would imagine.
Okay, so there are other, let me see. There are other kinds of analysis where I can put more ingredients here and include the whole point group symmetry. But for this purposes, the Martensites in this case, the only thing that's going to matter, especially to form those laminates, are the rotations of the variants. I cannot, for instance, invert a point or do anything there because there is a different variant going there.
Okay, well, I guess at some point you will show a free energy and then we can discuss it. Okay, so I'll go ahead and determine what the set of low energy symmetries for spectricals is, which is much more interesting. You can not only apply the rigid rotations, but all elements of a general Weil-Poincare transformation. Now, this builds on earlier work by Randall Kamian's group at Penn, in which they discovered a hidden Poincare symmetry for spectricals. Now, let me illustrate how one can start with a toroidal focal conic domain with a singular unit circle, and then apply this Weil-Poincare transformation to turn it into an elliptic hyperbolic focal conic domain with arbitrary size, eccentricity, orientation, and position. Now, just as a reminder, this Weil-Poincare group has all the transformations of the Poincare group plus dilatations. So you can start by applying a dilatation in your system, which will generally change the size of the singular unit circle. Then you follow this with a Lorentz boost, and depending on the parameter of your transformation, the velocity between quotes,
you can control the eccentricity of the ellipses and the hyperbola of this focal conic domain. Now, the next two steps are trivial. You apply a rigid rotation that will determine the orientation, and then a 3+1 dimensional translation, which will place the focal conics where we want them to be. So by analogy, here is the set of energy minimizers for the SMACT, where phi I are the variants that I described earlier, and WP is the group of Weil-Poincare transformations. If I now focus on the planar section, the energy minimizer simplified to the union of a translation in 2+1 dimensions of the up and down cones that I described earlier. So now comes to the last part of the theory of Martensites that I wanted to discuss, which is the compatibility conditions. So these crystal Martensite variants rotate and form twin boundaries in the form of planes or lines for the two-dimensional case. Now, this compatibility makes it possible that the crystal accommodate this deformation of the unit cell when the boundaries of the sample are constrained. Now, for the SMACT planar sections, the variant merge via conic sections that are formed in the projection of intersections between conic surfaces. Now, if these epochs here, or the events on using relativity jargon, are space-like separated, the intersection will form a hyperbola, but only if they have the same sign. Conversely, if the epochs are time-like separated, the intersection will form an ellipse if the two cones have opposite signs. Now, I can write down explicitly what the equations for these conics are using the group parameters that I described earlier. And here is what a combination of these cones look like for SMACT simulations, with the layers of the planar section shown at the bottom. What I'm going to do next is to use computational tools to decompose this SMACT section into domains corresponding to different variants. Here's the crystal Martensite that I showed before. You can interpret the light red as variant 1 rotated by a certain angle, and dark red as variant 2 rotated by a different angle. And then there is a very interesting mathematical analysis that you can use to explain all these fine laminate structures. And here's what the SMACT planar section microstructure looks like. The faint lines here that you can barely see are the layers, which again are perpendicular to this section. We color each pixel based on the parameters of this 2+1 dimensional translation group. And unfortunately, I do not have time to discuss the kind of clustering algorithms that we use to optimize the group parameters and separate the different regions into different groups. The blue lines represent the equations of the conics or the compatibility conditions that I described not too long ago. And you can immediately see that they are very consistent with the cluster decomposition. So to summarize, what I'd like to emphasize is that our theory not only unites two similarly disparate research fields, it gives concrete rules for combining the focal conics, explain all those regions that did not show an ellipse at all, and provide an intuitive and comprehensive explanation of this SMACT microstructure. Before I move to the second part of my talk, let me point out several interesting directions in which I think our analysis can be very valuable. Remember this figure I have shown at the beginning of my...
Before we go to that, if you go back to your
Sure.
picture for the Martensite,
Say that again.
see that, go back to your pictures for the Martensite. You can
This
see
one?
that they are strongly oriented along crystalline directions.
Yes. Mhm.
Okay, so it's not true that you have continuous symmetry.
That I what?
It's not true because the long-range interaction introduces frustration. You can actually have non-trivial length scales in the periodicity, essentially.
Okay, I see. I see what you're saying.
Ultimately, the regions actually are oriented along crystalline directions
Mm-hmm.
because those are the energy minima.
Mm-hmm.
And so you don't really have continuous symmetry in this case, as this picture shows. Compare the two pictures. The case of the actual smectic, in the case of the there you are essentially, you have a fluid in the continuum. It's a continuous fluid, and the only thing that matters are the boundary conditions.
Yes.
Near the at the boundaries of, the container.
That's
but
true.
all the interactions are short range, and there are no preferred directions because the vessel is isotropic.
That's true. Yes.
But in the case of the Martensite, that's not the case.
That's correct. Okay, I agree with you. Yeah, but yeah.
So there are no conic. I don't see any conical singularities, or whatever you want to call them here, in the case of the Martensite.
No, there are not conic singularities, of course. Yes.
Right. Okay.
No. Okay. So of course there are many things that are different between these two systems, and I focused on this interpolation of low energy configurations and the general ingredients that people used in the crystal Martensites. But as you mentioned, you're completely correct that there are features that are in the Martensite case that do not appear in our smectic case.
I mean, all the beautiful geometry that you discussed in the case of the liquid crystal is clearly not entirely relevant in the case of the Martensite.
I completely agree. And that's completely true. And the kind of ingredients that were brought from Martensites are applicable to smecticas, but the smecticas in some sense are richer because they have ingredients that do not have a parallel in the theory of Martensites. And as you point out, I totally agree with you.
Okay, thank you.
I'm not doing a one-to-one map here, but borrowing some concepts from the theory of Martensites to apply in smecticas, even though smecticas have this very different kind of focal conic defects that have no parallel in the other case. Yeah.
Okay.
May I ask you about the role played by temperature in the experiments in the smectics, if there is any? Because you have done, as was mentioned before, just gradient descents and not consider it
that's
at all. Then when you showed the Martensites, as Eduardo was complaining, I mean, the relation maybe is not the same because with the Martensites, you had this first order phase transition from the free energy that you showed in the sketch. So what's the role played by temperature in this smectic?
No, so that's a good point. In our case, our simulation was very simple. The temperature could be incorporated in things like the elastic constants that appear in the free energy, for instance. But it doesn't appear like a random kick like in a Langevin dynamics equation that we would consider for the dynamics of these systems. We do not consider any temperature variation here. So the only thing that we are interested in the general geometric structure that appears as to minimize this energy. Whether temperature is gonna play a role in the structure of this system, I'm not completely sure. I have to think more about this.
And the kind of transition that you would have in your free energy, the one that you're using, is it first order or is it second order?
So we don't consider the transition here. We're looking only at the structure. And I don't remember whether the smectic to kinematic transition is first or second order. I know that the isotropic kinematic is first order, and I don't remember. We're not focusing on the transition between the two, but
it's an example of a fluctuation-induced first-order transition. It's a very weak first-order transition.
For the nematic to isotropic, or also for the smectic to the nematic?
Smectic to nematic.
Okay.
It's analogous to the problem of the phase transition of the superconductor in a fluctuating gauge field. For the high-energy people in the audience, this is also known as Coleman-Weinberg. And in statistical mechanics is Halperin, Lubensky, and Ma. Okay, but the smectic to nematic transition is analogous to that by a theory by Macmillan and Dejean. It's very similar.
Okay.
Yeah. Very interesting. Thank you. Okay, so before I move to the second part, let me just point some interesting directions in which we we think our analysis can be very valuable. Remember this picture that I showed at the beginning. Back then, I was trying to give a simpler picture for what the defects looked like. But now suppose that the first layer here is not really a layer, but a hard boundary confining this magnetic liquid. It's then very easy to see that non-trivial boundaries can lead to a very interesting interplay between this extrinsic geometry of the confining substrate, the intrinsic geometry of these magnetic layers, and the energetic cost to compress or dilate the spacing between the layers. Now, these ideas are important to interpret many new experiments that report on exciting new structures, from what people call flower textures to patterns formed around Bourgeon defects and triggered by the flow through capillaries and things like that. We now have a powerful tool that can be generalized to provide deeper insight into this remarkable structure. But ultimately, what I really want is to explore new theoretical ideas inspired by a beautiful mathematical framework borrowed from optics, a kind of bifurcation theory in the context of singularities of caustics, which seems to map quite well into this magnetic problem. Okay, now, before I move on to the second part, I believe this is a good time to pause and ask if you have more questions for this part, because I'm going to shift gears. Okay, back in the day when I started grad school, I used to study this book on spin glasses by 3 scientists that are very renowned in the field of disordered systems, Mazzard, Parisi, and Virasoro. In a sense, I arrived somewhat late in the spin glass game. The so-called replica theory had been developed in the late 70s and early 80s. And even if I wanted to venture into the more rigorous mathematical results that backed that theory up, that problem had already been solved by Michel Talleyrand at the beginning of the millennium. Yet I would go to conferences and hear a lot about spin glasses and replica theory, and all of those words that I learned from this book. But many of the talks were not on the traditional diluted magnetic alloys that initiated the field. There were talks about neural networks, econophysics, protein folding, error-correcting codes. Now, in fact, my 1987 edition of this book already had a hint of the variety of exciting applications of spin glass theory, which is captured by the word beyond in the title. I brought that story up because I believe we are now witnessing a very similar phenomenon that originated in the study of glasses, amorphous solids, and jammed systems. What I'm showing here is an image that illustrates the onset of rigidity of an amorphous solids as it jams into a disordered configuration that resists compression. Now, what's really exciting about this is that the same framework used to describe jamming of spheres can be applied to a huge variety of other systems. It can be applied to cells in confluent cell tissues. It can be applied to strange quantum liquids, as we'll discuss later in this talk. And it can be even applied to systems outside the condensed matter world, such as machine learning. So as time goes on, we become more and more convinced that all of those systems are governed by a common framework that appear in the study of what we call disordered elastic systems. It's the main theme of the second part of my talk. I'm going to show how we can design periodic lattices with disorder to derive analytic and numerical results for 2 classes of disordered elastic systems near the threshold of mechanical stability, jamming and rigidity percolation. I'll then discuss their universal scaling behavior and exciting applications for colloidal suspensions, metamaterials, and even strange quantum liquids. But before I start, let me thank my long list of outstanding collaborators in this area. Now, let me give you a brief introduction of the kinds of systems that we study. In the traditional way of describing this ubiquitous transition called jamming, one compresses a bunch of frictionless spheres until they form a disordered contact network that resists compression. Now you can describe this rigidity transition by looking at the behavior of the elastic moduli associated with bulk and shear deformations, as the average number of contacts increases to above what we call the isostatic point of mechanical stability, ZC. And just as a quick reminder, it's traditional to decompose general deformations of an isotropic body into bulk deformations in which there is a change in the volume, and shear deformations which do not involve changes in the volume. At Z equals ZC, the bulk modulus jumps to a finite value, whereas the shear modulus grows continuously from 0. Using jargon from statistical mechanics, jamming seems to have this peculiar mixing of first and second order phase transitions. Now there's another widespread framework to describe a transition to a disordered solid that's very similar to jamming. It's called rigidity percolation. In this case, one usually starts with a fully occupied network, such as the triangular lattice shown here, and then randomly remove bonds. And bonds for us will be just harmonic elastic interactions, or springs, if you like. And as you keep removing these springs, the average coordination number Z drops to ZC, and the system exhibits a transition from an elastic to a floppy phase. As in jamming, the transition happens at the same isostatic point, but now B and G vanish continuously at ZC. The difference in similarity between jamming and rigid percolation leads to the inevitable question of whether or not it's possible to devise a unifying framework to describe both transitions. So what I'm going to do next is to show that this unifying framework exists, and that it not only reproduces well-known critical exponents, it has this major advantage of allowing us to extract analytical results in the form of explicit formulas for the universal scaling functions. Let me start by explaining our models and some of the main results we find. You have seen this figure in previous slides. What you have here is a combination of two lattices, the honeycomb lattice in blue and the triangular lattice in red. The honeycomb lattice has a finite bulk modulus and a zero shear modulus. That means that it resists changes in volume, but not shear deformations. I'm populating each bond of this latticing with probability PB here, which I take to be 0.9 in this figure. And just to be clear, what I meant by bond is just a harmonic elastic interaction, I spring. Now in turn, the triangular lattice has finite bulk modulus and finite shear modulus, and I'm populating each bond with probability Pn, which I take to be 0.2 here for this figure. Now the important thing is that I can control PB and Pn so that Z minus ZC is greater than 0, in which case I have a rigid phase, or so that Z minus ZC is smaller than 0, in which case I have a kind of fluid phase. But there's more. I can control PB and Pn to describe either jamming or rigid percolation. Remember that both of them describe transitions from an elastic solid to a floppy fluid, but that jamming has a jump in the bulk modulus. Now let's take a look at what we obtain for the behavior of the moduli near this rigidity transition as a function of PB and Pn. There's a lot going on here, so let me walk you through this. There's a floppy phase in this white region here, and a rigid phase above the red and green lines. Yellow represents the bulk modulus and blue represents the shear modulus. Dots represent simulation data and the surface represent our effect median theory results. And at this point, it's worth noting how good the agreement between these two approaches is. I'll say just a little bit more about the effect median theory in a few minutes, and much more if you come to my talk tomorrow in the afternoon. For now, just know that we have this analytical approach that reproduces quite well the critical behavior of disordered elastic networks. The red and green lines are rigid percolation lines. As you can see from them, both the bulk and shear moduli grow continuously from 0. And their terminating a rigid percolation line is our jamming point. So let me explain why we call it jamming. Suppose you build your lattice somewhere in this floppy region here, this X point, And now you randomly add bonds so that you approach the jamming point shown there. As you hit the jamming point, two things are going to happen. The average coordination number Z becomes equal to ZC, which, as I said before, is the isostatic limit of mechanical stability. And the bulk modulus jumps to a finite value. As you continue moving deeper into the rigid phase, the shear modulus continues to grow from 0. Now, 3D plots are usually tricky to interpret, so let me get rid of all those points in surface and just show a simpler phase diagram. This is a slightly different model in which I have two triangular lattices instead of just one. I was trying to figure at the top here. The universal properties of the jamming point do not really depend on such details, so I'll focus on the simpler case. Here, R and F denote the rigidity and floppy phases. And there is a jamming point J over there terminating this rigidity percolation line. I have already described the static elastic behavior, so you might be interested in knowing what other properties these rigidity transitions have. For instance, can we find a boson peak as we approach the J point over there? And the answer is yes, we can. And just as a reminder, the boson peak is a typical anomaly that's popular in the glass community, where it's often described as a rounded maximum in plots of the structure function. It's also connected to an enhanced population of low energy modes that leads to a flat density of states at low frequency. And so here what I'm showing is our calculation for the density of states for points approaching the jamming point from the solid to the dotted line. And the behavior is just as expected. This result is interesting to the jamming and glass community, but I'm mentioning it here just so that I can refer to it later when I discuss applications to strain metals. Now, our model describes several other dynamical properties that are observed in experiments and simulations of disordered viscoelastic materials, but I do not have time to discuss them here. And I'm going to say a little bit more about the universal scaling behavior displayed by the system. But first, let me go over what I have presented so far. By building on these periodic lattices, I can write down what, to our knowledge, is the first effect median theory for jamming at finite dimension. Along with numerical simulations and calculations for amorphous packets in infinite dimension and phenomenological scaling theories, I believe our theory gives a step forward towards a more complete description of the universal properties of these disordered viscoelastic systems. Now, let me tell you more about the effect median theory that I mentioned earlier. I have already told you about the phase behavior of the disordered elastic network models, but I have not emphasized what perhaps is the strongest feature of this approach. With effect median theory, we are in this rare position in which we're not only capable of testing universal scaling behavior, we have analytical handle of the singularities and can derive explicit formulas for the universal scaling functions. For these periodic lattices, what effect median theory essentially does is to replace the diluted network with spring constants k equals 1 by uniform lattices with spring constants kb and kn, which are chosen so that the dynamic response of the uniform system matches, between quotes, that of the diluted network. Now, by the end of the day, what we get are solutions for the effective spring constants kb and kn as a function of the probabilities pb, pn, and frequency omega. Now, if you recall the phase diagram that I showed you earlier, we can now explore the rich dynamical behavior of these solutions for points approach jamming over here, or rigid percolation from both the rigid and floppy phases. And more importantly, I can determine scaling variables for this system, like these two here, and then derive critical exponents in the universal scaling behavior for the spring constants. As you can see, these two variables are chosen so that both of them are 0 at jamming, but only delta PRP is 0 at rigid percolation. What I do next is to use these solutions to calculate space-time susceptibilities and then build a scaling theory based on them. So here is a scaling ansatz for the longitudinal response. In Fourier space, this is just the ratio between the longitudinal applied force and the longitudinal displacement. The main advantage of considering the dynamic response is that it's a very fundamental quantity in linear response theory. So if you know the exponents and universal function for chi-L, I should be able to extract the scaling behavior for a variety of different quantities. I could show results for the transverse component as well, but the longitudinal component exhibits a much richer crossover behavior that does not appear in the transverse part.
Sorry, please remind me what KL is. Is it susceptibility or what?
It's the susceptibility, yes. You apply a force. If you are in Fourier space, you can write your displacement field as this response function times the applied force. And then you can decompose that into a longitudinal and a transverse
The
function.
forces in this case will be the compression force or a shear.
For instance, yes, any kind. You can have a general modulation for the force, but yeah.
Okay.
So as promised, using effective median theory, I can derive the critical exponents and the universal scaling functions for the systems. Here, A, B, and C are just constants, and the plus or minus sign here correspond to the rigid and floppy phases, and this V tilde depends on the type of dynamics, undamped or overdamped, that you consider. Now, the equation on the red box is one of our central results. If these functions are truly universal, and there are some indications that they might be, knowing the functional forms for the scaling functions becomes as important as knowing the critical exponents insofar as universality is concerned. Now, that said, let me briefly discuss what else we can extract from these functions. This equation was derived for the behavior near this jamming point here, but it contains much more information. For instance, I can determine the universal scaling function for rigid percolation in general, simply by increasing the value of this crossover invariant scaling combination here.
Sorry, can I ask something? It's becoming too hard for me to follow. So are you going to explain this red box tomorrow?
No, not here. I do not have time. The red box is just we use effect median theory to write down explicitly what the universal scaling functions are. You remember, for instance,
it's mean field.
It is a mean field result, but then the upper critical dimension of these systems is thought to be 2, so it's fine. But the point is, you remember, for instance, the Ising model. You have M going as T to the beta, some universal function of T over H to beta delta, something like that. So that universal function is what we're really interested in. The explicit formula for the universal function. That's one of our main results. We can do some analogous thing here and calculate the explicit formula for the universal scaling function for the response. That's the main idea. But then to derive this, I have to introduce lots of other things. I'll comment on this tomorrow, but I'll not give all the details necessary to derive this. But anyway, that's the basic idea. We are able to use effect median theory in order to calculate explicitly what this is, what the functions are. And insofar as the upper critical dimension is 2, that should be good for real 2-dimensional or 3-dimensional materials. Apart from blobs that appear in 2 dimensions.
So is the relevance of the result the connection between the statistical model and the experiment, or is the solution of the statistical model? I'm a bit confused because mean field, normally when we solve a statistical model by mean field, if I understand correctly, okay, when it works, great, but it's some triviality, right? To solve it by mean field.
Okay,
what is the relevance of the result? Is it the mathematics of solving these statistical mechanical models, or it's the idea that these blue and red lattices have anything to do with experiment? Well, what is the interesting part of all this?
There are two aspects here. There are two aspects here. It's true that if you think of just the Ising model, mean field theory is trivial. But one clear example where mean field theory is not trivial at all is the spin glasses. spin glasses have a very complicated structure that emerges from mean field theory. And the same thing happening here. I mean, people have very nice calculations for mean field calculations or mean field-like results for these disordered elastic systems. It's not
Sorry,
true.
I don't work in statistical mechanics at all, but
No, that's fine.
I thought spin glasses,
just to conclude,
spin glasses, I thought was a good example where you could not apply mean field. Am I wrong?
there is a long controversy about applying mean field results to finite dimensional systems. And as far as I know, maybe Leticia could jump in if she wants. This has not been settled yet. There are people, for instance, like Fisher and Hughes, that believe that the mean field predictions are not applicable to two-dimensional, three-dimensional systems, but that has not been resolved at this point.
We are getting into a religious subject at this
That we are going to a religious subject.
No, it depends on whether you want to compare it to real experiments of real materials, or you're interested in the structure of the theory itself. So, you know, independently of whether you want to apply it to real materials, forget about that. But the mean field, the structure of the mean field theory of the standard model of spin glasses is interesting, and it has lots of peculiarities and weird, you know, features than they are interesting in themselves. And then they can be applied to other problems in math, in information, in, you know, so many other things where these appear. I mean, these are there because the problems are defined in field in nature. So my contribution to the...
But the point here is not that if the upper critical dimension is true, our mean field predictions are applicable to real materials. So that's one point. The second point is that we can write...
It's applicable for the exponents, but not perhaps for many other quantities, because above the critical dimension, even though the long wavelength theory is sort of trivial, in the sense that the exponents are...
Okay, so I do have a quick comment about that, because there was recently a paper by Eric Corring, where they seem to have shown that at least also the critical amplitudes are preserved from the finite dimensional case to the infinite dimensional case. So I'm not sure. It's an open question whether or not the things like the whole universal scaling function is preserved in mean field, and it's the same.
The exponents are preserved. This has been known for a long time.
The exponents certainly. But the functions.
But the problem is that the relevant operators are not irrelevant. In that case, cannot be. Except, I mean, they don't affect the exponents, but they affect a lot of properties of the phase diagram. I mean,
yes,
you expect the relevant operators to do.
That's true.
So.
Yeah. So the other point that I was going to make is that not only we have this mean field theory for jamming or rigid percolation that should be fine, except from logs that appear in 2 dimensions. But also we focus on finding out the explicit form for the universal scaling functions. And that's something new that most people don't consider and don't invest much time on that, because it's usually hard to do. So to respond to Pedro.
Sorry, can you comment, what's the range of validity of this formula? It's valid for small jam?
It's valid in general for points close to this jamming critical point here and low frequencies. So that's the range of validity.
I'm a bit confused by what's the, but then the universal scaling function is a complicated function, but it's all, I should only trust it close to that corner, or am I confusing?
I should trust it close to that corner, but there is a little bit more information on it, which comes from the crossover scaling idea. So even though I'm deriving it close to this corner, I can tell about the universal scaling behavior for this line because of the crossover idea. And I could make some pictures of the renormalization group flow for that we would guess for a system like this, but yeah, that would become too technical. But in general, I have confidence.
Maybe let me ask my question in a different way. I'm used to idea that we can fix exponents, but we can never fix more than exponents in an easy way. It's all, I mean, it's a miracle if we can do more than exponents. Can you do more than exponents? And what's the reason for this miracle in this case, if you can do more than exponents?
I can do more than exponents. I can do the scaling functions, exact formulas, analytical formulas for the scaling functions.
But don't they depend on the
the
details?
miracle is that it's a mean field theory. It's an approximated theory. So in the end, the fact that I'm able to calculate everything here comes from the fact that I'm using an approximated theory. Okay.
Can you, what's the imaginary part of the universal scaling function mean? Does it have a
The imaginary part, okay. That's the response function, right? So usually you have something like the dissipation. Okay, the imaginary part of the universal of this dynamic response has to do with the dissipation. You decompose this into a part that has to do with the energy that's stored into the springs, and then the energy that's dissipated due either to disorder or the fact that you have some viscosity around your particle. So the imaginary part has to do with this part of dissipation, and the real part has to do with the storage of energy into the springs or in the elasticity. Okay. Okay, so what I'm going to do is to take this invariant scale combination here, the crossover, to be large. That's typical crossover scaling behavior. And then I derive a simpler formula for the scaling behavior near rigidity percolation. And now it depends only on the two variables, u and v here, instead of this extra variable. And what happens here is that delta PB is relevant for jamming, but not for jamming, not for rigidity percolation. So in the end, the change in this universal scaling function must be accompanied by a changing of the critical exponents as I go from jamming to rigidity percolation, in order to accommodate this extra power of delta PRP from this invariant scaling combination here. So again, let me go over what I have just shown. With our effect median theory, we are able to reproduce well-known critical exponents, and more excitingly, write down explicit formulas for the universal scaling functions describing the behavior of the susceptibility near jamming or rigidity percolation. From that, I can derive universal functions and exponents for a plethora of different quantities, such as viscosities, moduli, correlation functions. I'm not going to do this here for the sake of time, but I'll just emphasize that this is a very general result with far-reaching implications. Now, Nathan, you said I could go over time. It's not a problem, or do I stop here? I could.
It's not a problem.
Wrap it up, or I can talk a little bit more about the applications.
How many more minutes do you want?
5 to 10 minutes.
Yeah, sure, no problem.
Okay, I'm sorry for going over time. Now let me start. Now I'm going to talk about a little bit about the applications. So let me start with metamaterials. And this has now become a buzzword describing anything from invisibility cloaks to shape-shifting materials that change from a flat sheet to the form of a face. Now, there are lots of very capable people designing materials with very complex and appealing properties. And for instance, what we see here happening from A to B is that I'm stretching this material along one direction. And unlike what we expect for regular materials, the other direction is also stretching. Now, these are called auxetics, as in the blue word here. And you should be able to find very many videos for a bunch of them on YouTube. Now, some people at Penn in Chicago developed this very interesting idea that you could cut bonds of a disordered lattice to control whether this material exhibits auxetic response or not. Depending on the protocol you use to cut the bonds, the ratio between the shear and the bulk moduli can go up, as it happens for an auxetic, or down, as it's the case of our regular material. Now, we know of two-dimensional isotropic lattices that lie exactly at the limiting boundary for each behavior. The honeycomb lattice that has G over B equals 0, and the auxitic twisted Kagome lattice that has G over B that's infinity. Now, if I can find a way of combining these two lattices, I can design protocols, which for us is just what kind of bonds I'm going to cut out, and then tune the mechanical response in any possible way in 2 dimensions. Here's what this kind of combination looks like. And these network models not only lead to a very simple and comprehensive tuning protocols, they also have interesting phase behavior that you can explore analytically. And that includes other kinds of exotic jamming multi-critical points. My second example is perhaps the most intriguing application of our results. I'm showing here the temperature doping phase diagram of a paradigmatic, strongly correlated quantum system, the cuprate high-TSC superconductor BISCO. And as you can see, there is an SM here corresponding to a strange metal phase near the top of this figure. I'm not going to discuss all the details that make this non-firm liquid strange. Instead, I'm going to focus on the unusual charge density response that these materials exhibit. Here's a plot of the measurements of the dynamic charge response spectra for this material, featuring a highly anomalous Q dependence. Apart from a magnitude that grows as Q square, the shape of the spectrum is largely momentum independent for most values of Q in this plot. If you're a glass person, this might trigger a connection with the boson peak, which I mentioned earlier in this talk. And in fact, here is a 3D plot of the universal function that we derived for the structure function as a function of invariant scaling combination for Q and omega near rigidity percolation, which also features a Q-independent bump related to the boson peak, here emphasized by the blue dashed line. Now, there are far too many caveats about this connection and too short time for me to discuss them here. Here I'm showing but a glimpse of some of the calculations we have for 3 distinct doping regimes and the comparison with experiments published in this paper. There are, of course, many features that cannot be captured by our simple model. What I want you to remember is that rather than simply fitting experimental curves, what we have here is an alternative way of interpreting dynamic response data for these strange metals using well-known ideas from the jamming and glass literature. Now, in my last few slides, I'll briefly discuss connections with what we call shear thickening.
Sorry, I have to go back to that since I'm very familiar with that experiment.
Mm-hmm.
There is nothing out of equilibrium in that experiment.
That's true, okay.
This is nothing glassy in the system.
Okay. The analogy with glass system
and with jam systems
is the jam system don't need to be out of equilibrium in some sense. That we're not interested in the particular feature that you have some slow dynamics as you enter into a glass phase or something like that.
Okay, this is
we are interested in the what makes the connection between, for instance, jamming and the glass system of the boson peak between jamming and glass physics is the fact that you have marginal stability. If you have a system near jamming, you cut one bond and you have a soft mode there. And right, that's marginal stability.
Stability means that you're in some kind of crystalline state.
Oh, yes, that's
crystalline about the strange metal.
It's amorphous. It's amorphous, but it's
not. It's a liquid. There's nothing amorphous about it. It's a liquid. It's a strongly correlated electronic liquid.
No, say that again.
The strange metal is a strongly correlated electronic liquid. There is nothing amorphous.
I agree. No, I agree. I'm not saying I have to be careful about making the precise connection. I'm not saying that it's we're not saying that this is going to be a solid or an amorphous solid or anything like that, but that it has signatures from the boson peak due to some sort of marginal stability in the system that might be growing up, leading to low energy, a population of low energy configurations.
Well, there is something which is marginal that naively for sure in the regime where this is actually, where the spectrum is flat, then it fits a phenomenological theory known as the marginal Fermi liquid, which is essentially the limit is where the Landau theory of the Fermi liquid begins to fail. Okay, in that sense, it's marginal. But there is also a regime where it doesn't fit that when you go to lower frequencies. And there's nothing marginal about it. And there is no explanation, as far as I know, of the behavior that is seen in the experiment. But there is nothing crystalline.
Okay, I'm fine with that. Okay. But then, even if you look at the jamming point, let me see if I found the phase diagram.
Right.
Even if you think of this, you can have the behavior approaching the critical point here from the liquid phase or from the floppy phase. It's not elastic, it's not crystalline or anything. And it still has a boson peak there. It still has this signature.
Well, anyway, anytime you're close to a continuous phase transition, you will get very strong scattering, of course.
Yeah.
And that's, you expect that. You get fluctuations. Even though here is in field theory, there are still fluctuations.
No, yeah,
that's what the boson peak actually means. But
yeah.
But on the other hand, your jam state is actually more like a glassy state. There is nothing glassy here.
That's correct. I mean, there's no dynamics. There's no slow dynamics. That's true. That's true. That's true.
So I think
I agree
you
with
have
that.
to be careful with. I mean, you can always fit data. You have to be.
But that's not what we're doing. Yeah. Okay. I completely agree with you. That's not what we're doing. We're bringing up these ideas of the boson peak to this other community that might help to give a new point of view into interpreting these experiments.
Okay.
But I totally agree that it's not I'm not saying that the electrons jam or anything like that, but that there is a connection with the physics of jamming that might be useful to help understand and interpret the
interpretation is that there are no electronic quasi-particles there because they are very broad on the scale of the energy. So the quasi-particle picture is actually the distinguishing feature of the strange metal is that the quasi-particle picture is not applicable. So you cannot do, for instance, Boltzmann transport theory there, for example. And so you cannot explain any of this using Boltzmann transport theory. And this is a measurement of the density correlation function. That's what it is.
Yep. Yep.
So, okay. So
okay. Okay. Yeah. No. Okay. So I'll go to my last few slides and I'll briefly discuss connections with what we call shear thickening, which is this behavior of certain colloidal suspensions in which, roughly speaking, a fluid under stress behaves like a solid. So that, among other things, people can walk on the water. And if you have not seen this before, you can check the videos on YouTube. This phenomenon is simple to describe. You apply a shear stress on a colloidal suspension and it thickens, meaning that the viscosity increases abruptly by an order of magnitude or so, sometimes even discontinuously. So the phase diagram in terms of stress and volume fraction has a region of continuous shear thickening, a region of discontinuous shear thickening where the viscosity jumps, and a jammed region. I've recently been part of a team that proposed a phenomenological scaling theory to explain extensive experimental data on solutions of cornstarch in glycerol. Now, the challenge aspect here is that it can happen even far away from the jamming critical point. So it's surprising that one is able to produce such good scaling collapse of data like the ones I'm showing here. I'll not discuss the details but just briefly mention our attempt just to tackle this problem using a microscopic calculation. An important feature in these systems is the formation of force chains, which lead us to consider the role played by anisotropy in the response of these viscoelastic materials. And for this end, we can imagine populating bonds in a simple triangular lattice and having the probability depend on the orientation of the bond. We have been exploring both the phase behavior and dynamic response of this system. And without going into any details, we believe that the inclusion of microscopic mechanisms of anisotropy, along with other features that I have not time to discuss them here, has the potential to clarify some of the deep questions regarding intriguing new results for shear jamming and thickening. Now let me close this part by emphasizing that our formulas for the universal scaling functions not only allow a quick assessment of scaling invariant behavior for quantities such as viscosities and correlations without the need for computationally expensive simulations. They also serve as models even for systems for which the universality class has not been determined. Now let me conclude by reminding you of the little story I told you at the beginning of this part of my talk. I mentioned spin glasses and how their theory had later permeated a gigantic variety of different systems, from economics to biology and more. In hindsight, part of this is due to the fact that quantity disorder and frustration, which are the two most popular ingredients of spin glasses, are really everywhere. Now, as I mentioned earlier, there seems to be a similar mechanism at play for these disordered elastic systems. And I feel very fortunate that I'm able to learn more and participate in these developments as they take place during our time. Thank you very much for your attention.
Okay, thanks very much, Danilo. So maybe people now can raise their hands just to make it a little more ordered. And then, of course, you can interrupt. I mean, if somebody asks a question and you want to follow up, that's fine. But just maybe if somebody who wants to raise their hand who hasn't asked a question before, or if not, we'll just make it anybody can ask.
I asked too many questions already.
No, Eduardo, there's no such thing as too many questions. Just some people, they save the questions for the end. Nobody's raising their hand, so anybody can ask. So go ahead.
So maybe I can ask something that's very general. I mean, the field is actually very far away from what I know. But I'm wondering, well, maybe you're going to talk about it tomorrow, but I'm wondering, so what are the theoretical methods that you use in your descriptions and your results? I mean, the first part, of course, you use some numerical methods, and the second part, but a little bit, so it's field theory or so do you write, I mean, Navier-Stokes equations, or what are in general the methods and how?
Okay. So in the first project, the SMACT project, we made a combination of elasticity theory, which is a field theory, and numerical simulations. So that's not a very common approach in this field. People usually start with some molecular dynamics for the particles and orientation of the molecules and things like that. In our case, we have a coarse-grained approach, a field theoretical approach at the beginning, and we simulate that. So we derive the Euler-Lagrange equations for those systems, and we evolve it using a numerical method.
And so here the difficulty is more in the finding these equations or deriving this equation, or
deriving these equations.
No. Okay,
deriving these equations, they are more or less a standard, and many of the results are a little bit independent of the kind of model that we're considering explicitly. So the subtleties appear as the solutions, the numerical solutions of the equations, and the analysis of the solutions of the equations. That's where the subtleties appear. Now, the second part of my talk, I'll discuss in more details tomorrow. We use this effect median theory, which involves some sort of mean field approximation. But that's not very trivial, and that it has an advantage that it preserves the topology of the lattice. That's something that's important for us, because we are interested in having a finite bulk modulus, as I explained. So yeah, the main idea of this effect median theory is that you can replace the disordered, diluted network by an ordered system with a uniform lattice with a spring constant that are given by some set of self-consistent equations. The way we do that, I will explain tomorrow. But based on that, I can derive many different analytical solutions for that, and that includes the scaling behavior that I described earlier.
Can
Okay.
I ask a question
Sure.
concerning this? This is, I mean, what you just described is the reason why effective medium theories are usually presented. On the other hand, in systems which are disordered, you have to worry about, let me call them unusual events or rare events. The probability distributions near these phase transitions are not usually Gaussian, and you may get multifractal behavior and things of that sort.
Yeah. Okay. That's a good point.
So how robust is this type of analysis?
That's a very good point.
To such, more general analysis, which is what you expect in a disordered system.
Yeah. No. You raised a very, very good point. Okay, I do not have the plot here with simulation points, for instance. But what happens is that real systems, if you simulate these lattices, for instance, there will be some regions that has to do with the disordered mechanism that you were just referring to. There will be regions that will be over constrained. There will be regions that will be under constrained. And the threshold will not exactly follow the exact threshold that we have in the effect median theory. So one of the consequences of having the effect median theory is that we might have some discrepancy between the simulation and for the actual threshold here that you get.
Do you expect to see a Griffiths regime?
Oh, I don't know. I've never thought of thinking about the Griffiths regime here. Okay, I don't know. I have to think more
rare
about it.
events dominate essentially, and
Yeah, I don't know. I have to think more about that. But the only other thing that I was going to mention is that near this jamming point, the simulation and the effect median theory agree quite well. And part of this is because this jamming point is very special. And there are concepts that it would take me time to go over if you have not heard of that before, like the states of self-stress that you have in the jamming point. And in the jamming point, you have only one state of self-stress that governs the entire system, that permeates the entire system. And that makes this, that kind of controls these different fluctuations that appear that are responsible for the discrepancy out here and make the approximation better near this jamming point. On the other hand, for this simple system, we never found something very different for the exponents, for instance, and the critical behavior in general. There are other extensions of these models to describe, for instance, fiber networks where you have bending forces, where effect median theory fails miserably and doesn't even give the correct critical exponents. But for our simple mass spring system, it's usually good, especially close to this critical point in this jamming point. But yeah, you raise a very good point, and yeah.
Can I ask a very naive question? So I'm still a little bit confused because, as you explained, these fields are huge and there is so much, there are books and so on. And I see from the outside, I see here two important steps. One is understanding that these blue and red lattices are important and formulating some statistical mechanical models on these blue and red lattices. And the second step is solving them using mean field theory, perhaps, or whatever. And that's a mathematical problem. So can you just tell us what was your contribution, or did people know already that these models, was that a part of review, and
No.
people knew already that the models were
No.
the relevant thing, but no one knew how to solve them? I doubt.
No,
right?
no. Okay. Coming
Well,
up
what
with-
exactly did you do? Because I could not distinguish the review from the new stuff.
Absolutely. Okay. I can tell you clearly what exactly I did. So this didn't exist. People didn't know a combination of lattices that would describe both jamming and rigidity percolation and the connection between them. So there were calculations, for instance, there are very good calculations for jamming for models in infinite dimension. And this using the replica theory that was developed for spin glasses, for instance. But there were not calculations that describe jamming with a finite bulk modulus at finite dimension. And that's one of my main contributions, coming up with this idea of combining honeycomb and triangular lattices.
Okay.
Because the honeycomb
Okay,
has
that
bulk
sounds-
modulus and things like that.
Okay, that's nice.
And then, of course, the methods that we applied, I mean, we have to be careful about applying it and doing the calculation carefully, but they were standard. And there were other calculations that did that.
Okay. Okay, no, that's good. I mean, yeah, that indeed. Thanks.
No problem.
Any other questions? So we'll hear another seminar from Danilo tomorrow, and anybody who wants to talk to him individually after, just send me an email and I'll set up with Danilo a time when you can talk to him individually. So probably it makes sense to do that after Tuesday.
Thank you.
Oh, see you tomorrow. Thanks a lot, Danilo.
Thank you.
Very
Thank you.
much.
Thank you.
Thanks,
Bye-bye.
everybody.
Thank you.
Thank you very much, Danilo.
Nathan,
Yes.
do you have a few minutes to chat?
Yeah, sure.
Okay.
I'll leave.
Recording stopped.